Okay, so we've got one last discrete random variable to talk about, and that is the Poisson random variable. Poisson is the French word for fish, but I think it's a guy's name, is why it's called that. And we use the Poisson random variable to model counts the same way we do like binomial or potentially hypergeometric random variable, but it has different parameters. Okay, so the parameter for the Poisson uh, random variable, there's just one. It's lambda here, and it's like the average number per period. Okay, so when we get information in the form of a average number of occurrences, that's probably a tip off that a Poisson model is a pretty good way to think about it. Um, and I shouldn't be too attached even to it being a time period. It can be the uh, number of events in a period of time. So like the number of shooting stars per hour or the number of earthquakes per year, or, but it can also be defined with respect to an area, the number of suicides on campus, the number of typos on a page. These are all things that people have modeled with Poisson random variable. The Poisson random variable does have the idea that each occurrence is independent of previous ones built into that. And really with all those examples, you could think of reasons why they might not be independent, but as always, we're sort of weighing the advantages of using a random variable that's nice and easy to work with against the inappropriateness of independence assumptions. So if you're, you might want to define it as the number of shooting stars that you see per hour on the peak night of the Perseids in Joshua Tree, and then you sort of condition the random variable itself in a way that maybe makes independence a little bit more plausible there. Anything that is binomial can be modeled as a Poisson random variable. Okay, so any binomial random variable we can treat as Poisson just by letting lambda equals NP. Okay, so that would literally would be the number of expected successes in n trials. Sometimes we use the Poisson random variable when it's not like clear what a trial actually is. Like in the shooting stars example, would a minute be a trial? Well, no, it's not, because you could actually have more than one per minute. Same with the earthquakes, that kind of thing. But even something that, truly, what the trial is, and you are thinking of it in terms of number of successes, even if you know it's truly binomial, you might want to use a Poisson random variable anyway, because the Poisson is easier to calculate the probabilities. It's easier to work with in several ways. And one, especially when you get a large n and a fairly small p, the Poisson PMF, like if you graph out these values, it's almost identical to the binomial. And later in the quarter, we're going to do a little R problem that models things that could be thought of as binomial as Poisson, and you'll be able to see how close they are. I think actually we might be able to do that in the workshop for this unit as well. Yes. Okay. A couple of other kind of obvious points. So the parameter of the Poisson random variable is its expected value. And like that's kind of the usefulness of the Poisson random variable. A lot of the times that's the information we get, that the sort of the average rate is something. And so that's knowing the average rate, thinking of as Poisson, allows us to calculate the probability of specific values. That's super helpful. Less obviously, it's also true that that same lambda ends up being the variance of the Poisson random variable, which is a fact. I'm not going to say too much more about that here. I think I'll just work through a short kind of example of Poisson. It's in some ways it is a more straightforward random variable, just a matter of plugging in one parameter and the appropriate support values to calculate probabilities here. Okay, so the example I have in mind is, let's say that we're thinking about the number of earthquakes per year, and let's say there are on average one major earthquake. So let's think about this as a kind of an earthquake of, say, greater than magnitude 6 every 4 years. So we could think in terms of 4-year periods, but the Poisson random variable is so nice. It lets us, if we want to think about per year, that's on average an expected value of 1/4 per year. And that would be the lambda value for a Poisson model to capture this. And so with that, we can just go ahead and calculate the probability that we have 0 earthquakes in a year. If we're getting one on average every 4 years, that's plugging in 0.25 for lambda and 0 for I. We get e to the negative 0.25 times 0.25 to the 0 power divided by 0 factorial. The kind of arrangement of the e's, the zeros, the factorials, everything looks a little bit weird here, but just be brave and work through it. The important thing here is to make sure that you're getting the lambda in the lambda position. So yes, lambda is here in the exponent of the e, lambda is here being raised to the power I, and here is I factorial down here. 2 things to remember, easy to forget, is that 0 factorial is defined to be 1. And it's defined that way because the kinds of situations which you're using factorials are like this one, where it's useful and makes sense and fits into the broad pattern if we define 0 factorial as 1. And similarly, that any number that's not 0 raised to the 0 power is also 1. It's not equal to 0. Means that we've got kind of a whole lot of 1 going on here. This whole, this is equal to 1, that's equal to 1. So all we've really got is 1 over the e to the 0.25 power. Punch that in the calculator and it gives us a pretty reasonable looking probability. 7779, okay? So pretty likely that in a given year, there's 0 earthquakes, and you just kind of think about that baseline rate of 1 every 4 years. Yeah, we should get a pretty high number there. Let's look at the probability that we have 1 earthquake in a year. We've got the same E.025 thing there, but now we're multiplying it by lambda to the 1st power because I equals 1, and dividing it by 1 factorial. So that's just taking 0.25 times the number we got before, and that is 0.195. One more. What's the probability that we have 2 earthquakes in a year, given that we have 1 on average every 4 years? Same, e to the 0.25. So I'm just noticing that this part of the PMF doesn't depend on I, it's always the same, times 0.25 squared divided by 2 factorial, that's 0.24. And then the probabilities are going to decrease from there. Those look like reasonable probabilities, right? For something that's occurring on average every 4 years. 1 every 4 years. Okay, so that this kind of context is, I would say, very common use of the Poisson distribution. You get information about an average rate, and you can calculate probabilities of specific numbers of occurrences in a given time period. The last thing I'll say here, and kind of to close off our discussion of discrete random variables, I think for many of you, you might be, when you're looking at the Poisson PMF, that's finally something that actually looks like a function. These kind of tables that we were doing for the ad hoc random variables, and the kind of wild expressions with all the combinatorics that we had for our Bernoulli oriented random variables. This is looking more like what we think of as a function. We plug in the domain value, the argument, which is always in this case the outcome whose probability we're interested in. So you tell me how many earthquakes you're interested in, I'll tell you the probability here. That's what the function does for us. And now, and the only thing that might still seem a little bit odd about this is that we've got I rather than X as our argument. It's just notation, but it is notation that's meant to remind us that the Poisson, like the binomial, hypergeometric, like all of these random variables, only takes non-negative integer values. Okay, it doesn't take fractions, no irrational numbers, nothing like that. That's going to change with the next unit and the next lesson, when we're going to start talking about random variables that can take any value on the real line, or that will have support that's a subset of the real line. So I'll see you then.